and I am recording. So let's see here. Today, I just want to check something real quick, with regard to our progress in the assignments. What week is this? Okay, yes. 18 through 21. All right, so I'm basically a week behind. Awesome. All right, so at the end of last lecture, I made a comment about what you could do on assignment number 3 that was made in ignorance because I hadn't actually looked at the assignment questions yet. So lecture set number 5, which is the one that we're essentially done lecture set number 5. I just had a couple of more comments on the normal probability plot, which I'll get to momentarily, and then we will be done with lecture set 5. Assignment number 3 is lecture set 5 and lecture set 6. Fortunately, lecture set number 6 is actually quite short, and it's basically just let's say 2 very important definitions, and then exercises that are directly related to what we had just done in lecture set 5. So 2 important definitions, and then an application of the techniques that we had just learned about. So from that standpoint, it's not a big leap forward, which is nice. And again, it's a pretty short lecture set, so I'm confident I'll probably finish it today. But I keep saying that and then I'm wrong. So finish most of it today, I guess. Anyways, so for assignment number 3, lecture set 5 is question 1, 2, 3. And then questions 4, 5, 6, 7, 8. That would be lecture set number 6. But you can, if you've looked at the assignment, you can see like question 4 is just a restatement of one key definition. Question 5 is a definition. Question 6 is a question that basically asks if you understand the definitions that you wrote down in 4 and 5. Question 7 is a definition, and then question 8 is application, and we'll see an example of that today. And then part B is obviously the lab part, but my guess is that all of the lab material has been covered already. So once we get through lecture set 6, we can finish this assignment, which is good. According to the course outline, course outline, I'm about a full lecture behind right now. So it's not terrible given where we are in the semester. And we have midterms coming up the first week of November. So we're in week 7, week 9 is the midterm week. So not next week, but the week after we will have midterms. So I'll have to send out some more information about the midterm and post all the practice problems and the practice tests and whatnot. I'll get to that before the start of next week so that you guys have that material. And when I post the information, I'll let you know like what lecture sets are going to be covered and what you can expect in terms of questions and things like that. But again, I have lots of practice material for the midterm that I'll post, so you guys will have lots of resources for getting ready for it. Okay, so with that being said, we should probably keep going with the lecture material. So I'm going to start just by, I just want to go over the normal probability plots again, real quick. I think actually in looking at the assignment, this is probably not even. Oh no, there is one question that would use this in part B. So it's not a complete waste of time. So that's good. All right, a normal probability plot. What is it? Why do we use it? Well, it's a plot, a scatter plot, and it plots the observed values in your data set against a set of normal scores. And actually, it doesn't matter which axis you put the values on, the relationship will be the same. But we've been putting the normal scores on the y-axis and the observed values on the x-axis. So for example, on slide 39, we have a data set that has 6 values in it. And we have plotted those 6 values against the normal scores that we picked out of table 3. So you might recall from last class, table 3 is a table where you have only sample size as the variable that changes. So all you have to do is identify your sample size and then take the normal scores that are associated with that sample size. So that looks something like this. Right? And you can see, for example, in our illustration, we had 6 observations. So we are just taking this set of normal scores here. Right? So if you pay attention to the values here, you can see that it's I'm directly pulling those normal scores and I'm ordering them, or I'm assigning each normal score to a value in our data set. And the key is that I order the values in our data set. So I'm running now from 2.66 to 12.56, and I'm aligning those values with the normal scores. All right. From there, we're just creating a scatter plot. And what we are doing with the scatter plot is using it to determine whether or not the relationship is linear between the normal scores and the observed values. So if the relationship is linear, that indicates evidence of normality. If the relationship, well, sorry, the actual language is, if the relationship is linear, that indicates that there is no evidence that the variable is not normal. And if the relationship is nonlinear, that would indicate evidence that the variable is not normal. Okay. This particular example is a tricky one because there's actually 2 arguments that you could make. I've said that this is normal with an outlying point because the majority of the observations fall along the straight line. So we have 5 out of the 6 values falling along that straight red line. But if you're being really strict, you could say this is actually more of a right skew relationship because of that outlying point would kind of drag. You might say we only have 6 values, we need to pull more, but what if this outlier isn't an outlier? It's actually representative of the tail of the distribution. And in this case, we have more of a right skew. So this is where the subjectivity of the plot comes in, and it can become difficult to make a determination about what the plot is actually telling us, which is why we can develop hypothesis tests for normality, but this is something that we'll talk about later in the course. Anywho, the point is, when you construct a normal probability plot and you're making your argument about whether or not it gives evidence for or against normality, you do that based off of linearity. If you don't think the plot is linear, as long as you reasonably describe why you think that this is the case, you can still get full marks on an assignment or on a test. The key, though, is using the plot correctly and giving strong evidence in either direction. So giving strong evidence of what you think the plot is communicating. All right, now from a normal probability plot, we can also assess whether or not there are potential outliers in the data set. This again is somewhat subjective, but the idea here is basically, are there observations that fall far from the majority of the values? So in the previous illustration, I think that most people would probably agree that given the 6 values, this point that I have circled in red is an outlier because it's quite far away from the bulk. But again, there is some subjectivity there. Okay, so here are some different examples of situations where you could outline an outlier or maybe say that there's evidence of skewness. So the first one, again, this is one where we could go either way. So you might say, because of this second point, that it's reasonable to assume a relatively skewed pattern in the data set. But one might also argue that if you draw a straight line through the data, the majority of the points fall relatively close to the line. So this here could be an outlier. Now, even if this is a skewed relationship, which might be a more appropriate representation of this particular data set due to this point here. So if this is a skewed relationship, and this observation here kind of makes this more likely, in my opinion, because it makes this outlier point a little bit closer to the group, as this is fairly sort of in the middle of the two. This farther point, I would still suggest as being a potential outlier, even if we have this second point here, because it is quite far from the bulk. But the question of linearity does come into play due to these two outlying observations. Yeah, Michael, I just said that like 5 times, man. All right. Okay, second plot, it's the same idea, and like this is just subjectivity over and over again. So here we kind of have what we would describe as an S pattern. So this particular relationship is an interesting one because this indicates symmetry, but it also indicates what we would call heavy tails. So whenever we see an S pattern, like the one shown here in a normal probability plot, that indicates a bell curve, so symmetry, but it indicates that the tails are heavier than a normal distribution. So this would be what we would call a T distribution, and we'll also talk about that later. So in this particular case, we again would say this would most likely be non-normal. And you might flag those 2 points as potential outliers, but I think that those are more likely just kind of, well, I guess you could flag them as potential outliers with reference to the normal distribution. Okay, in number 3, we have a pretty good plot. There's a little bit of tail activity here. So we might rate slightly heavier tails. But for the most part, I think that this plot looks pretty good, and you could probably make a reasonable argument that that we have evidence that we have no evidence that the variable is non-normal in this case, because for the most part, the observations fall along a straight line. And that's the same situation in number 4 here. So this plot would be ideal. You can see here that we really don't have any kind of extreme values. We don't have anything that would be considered heavy in terms of the tails, and all the points fall quite close to the line. So this would be no evidence of non-normal variable. But again, the point is that what we are doing is we are assessing linearity between the normal scores and the observed values. So if that relationship looks linear to you, and be reasonable with that. Like if you were to argue that the second plot is linear, that would be a difficult case to make. But in the last 2 plots, that would be a very reasonable conclusion to draw based off of what we are observing when we plot the normal scores against the observed values. But if the relationship is not linear, that would mean that there is no evidence of normality. And if there are points that fall far from the pack, so for example, in the second plot, we have these 2 outlying tail values here. And in the first plot, we have this extreme outlying tail value. Those would be potential outliers because they're far from the rest. So that's all we're looking for when we use the normal probability plots, points that are far from the pack and linearity. Those are the 2 big things. And one last comment. Just because the observation is far from the pack doesn't mean that it is an outlier, okay? It's a potential outlier. We would have to then go and evaluate whether it's an outlier using other measures, which we aren't going to learn about in this class. Okay. Any questions regarding these plots? The intercepts. What do you mean when you say intercepts in this situation? No, I wouldn't really consider, like in this particular situation, I wouldn't really think about this in like a traditional linear modeling sense where you have like X and Y intercept values. Like I understand like what you're saying, like you could calculate them, but they don't really have any meaning because we're just looking for a trend and it doesn't matter what the specific values are in terms of like intercept and slope. Does that help? Okay, sweet. All right, so that brings us to the end of lecture set number 5. Again, the lecture set number 5 is focused on working with the standard normal table. So we learned how to find area underneath a standard normal curve using the normal table. We learned how to find z-scores, so percentiles of normal distributions starting from area under the curve. And then we extended those two techniques to the case where we are working with any normal curve. At the end, we talked about the normal probability plots, which are used to evaluate normality. In lecture set number 6, we're going to talk about normality in a different context. So the main techniques that we are going to learn in this lecture set follow directly from what we learned in lecture set 5. So we're still going to be working with the normal table, and we're still going to be basically computing z-scores, but in a slightly different flavor with a very small modification. Now, the rationale for why we want to do this is based off of wanting to understand how the sample mean behaves. So the idea is we have some population that we want to talk about. So, perhaps you want to measure, like average GPA of all university students in the country. In order to do this, you need to collect a sample, and then from the sample, you need to build an estimate. So if we want to estimate the average GPA score of all university students in the country, based off of our sample, the most reasonable value to compute would be the sample mean of GPA scores of the students that we have actually observed. Okay, the issue, or one of the key issues that we are going to face when we do this, is our sample is only a subset of the population. So you might recall from lecture set 1, I sketched a little graph that looks like this. So I had my box, which I called the population. And then I drew a circle inside the box, which I called sample. And this could be like sample 1. We can repeatedly sample from the population, but this would be one sample. So the sample is clearly just a subset of the population, right? It's not covering the entire box. It's only covering a portion of the box. So as a result, when we build or when we compute a statistic from the sample, so we collect our sample of say 300 students, and then we calculate X bar for those 300 students, there's going to be an error associated with that statistic. because it is based off of a subset of the population. We call that error the sampling error. So the sampling error is an error that is associated with any statistic that is computed to estimate a population value. All right. So assuming that everyone agrees that this error would exist, so acknowledges that this will be the case, what we would like to do is be able to account for and describe this error. So that's actually the main goal of this lecture set, is to first acknowledge that there will be this sampling error that has to occur because the sample is only a portion of the population. And then to say, okay, I accept that this error is going to occur. How can I account for it? And how can I describe it? Okay. To account for the sampling error, we define what is called the sampling distribution. In general, a sampling distribution is the distribution of a statistic. We have seen a lot of examples of distributions so far. In lecture set number 2, we actually talked about describing the distribution of a data set using histograms. So you might recall that our descriptions of distributions are based off of symmetry or skewness and modality. So those were the two key aspects that we were, or the two key descriptive terms that we were using to describe the distribution of a data set. Now what we are doing is we are taking that same idea, but we are extending it to a statistic. So essentially what we are saying is, I can collect a sample, and from that sample, I can build a statistic. The sample will have its own distribution, and the statistic will also have its own distribution. Okay. And the sampling distribution refers to the distribution of the statistic of which I have calculated. Of the statistics that I have calculated. Now for us, the statistic that we will be interested in describing through the majority of this course is the sample mean. And there's a lot of reasons why we focus on the sample mean, but to keep it fairly short, the sample mean has good properties. So it's a good estimator. All right, so in general, the sampling distribution is the distribution of a statistic. The sampling distribution of the sample mean describes the distribution of the sample mean. All right, so to try and better understand this idea, I'm going to illustrate how this might, how we can interpret this from a visual context. Okay, so suppose I have a population. All right, and let's suppose, just for simplicity's sake, that this population follows a normal curve. Okay. We'll talk about a situation where things aren't normal a bit later, but let's just assume that this is my population distribution. And this is a normal curve with mu and sigma. Okay, so my distribution, or the population that I am studying, is normally distributed. It has a mean mu, and it has a standard deviation of sigma. Okay. All right, now let's suppose that I start sampling. Okay, so this is going to be sample 1 values. Okay, so that's going to be X bar 1. Okay. Now, effectively, what's happening here is I can just keep repeating this process. So I collect one sample, I compute X bar. Then I collect a second sample, I compute X bar. Then I collect a third sample, I compute X bar. And I can do this as many times as I want. Oh, that's not 4. Okay. So in this illustration, I started with my population, which was normal. I collected one sample. I computed X bar 1. I collected another sample. I computed X bar 2. I collected another sample. I computed X bar K. And then I ended up doing this, or X bar 3. And then I ended up doing this K times. So I've collected K samples. So I have K sample means. All right. K is just some constant. So it can be like 100. I collected 100 samples. Or K could be 300. I collected 300 samples. All right. Now, each of the samples you can see, they have a distribution based off of the values that are in that sample. Then what I can do is I can take all of my sample means and I will have another distribution. So these will be sample mean values. Okay. And this is going to be, and this will have, this is the sampling distribution of X bar with its own mean and variance. Okay, so that's the initial idea. Again, like from the beginning, it's basically, I have a population I want to study. I collect a sample. From the sample, I compute a statistic, X bar, for example. I acknowledge that there's going to be a sampling error associated with X bar. I want to be able to account for the sampling error. So I can study the sampling distribution of X bar. So the sampling distribution of X bar is going to allow me to understand the sampling error. The sampling distribution is the distribution of the statistic. So this would exist under the acknowledgement that I can repeatedly sample from the population. Okay. Any questions so far? Okay, so just real quick, again, I've written here, so this last image, this last curve is the sampling distribution, and it has its own mean and variance. So now what we need to do is understand, okay, or what we need to do is say, I understand what the sampling distribution is, what are the mean and the variance. So the next two examples are simple illustrations of what happens or how, it's better to say it like this. The next two illustrations are very simple examples that describe how the mean and the variance of the sampling distribution behave. Okay, so suppose you have a population with only 5 values in it, right? Again, very simple illustration. So you have a population with 5 values. The mean and the standard deviation of the population are 3.386 and 0.545. So the mean here is just the mean of those 5 values, and the standard deviation here is just the standard deviation of those 5 values. So those are the true values of the population, which in general we don't know, but for illustrative purposes right now, I'm using them for illustration. So we have our population, which is size 5. We know the true parameters, which are shown here. Now let's suppose that for whatever reason, we can only collect samples of size 2. All right. Since I have 5 values in the population and I'm collecting samples of size 2, there are 10 possible samples that I could observe, which is 5 choose 2. So those 10 samples are listed in the table below. Okay, so you can see I have the sample number and then I have the values that are in the sample. For each of the samples, I compute X bar. So I'm just taking the average of the values in each sample. Okay. Then what I'm going to do is I'm going to compute the average of all of the sample means. Okay. So here I have average of all sample means. Okay, and that's found in the same way that any average is found. So I have my 10 sample means, I just add them all together and I divide by 10. Okay, now what I'm going to do is I'm going to compute the standard deviation of the sample means. So I'm going to take each sample mean, I'm going to subtract the average of all of the means. So that's what's happening here. So difference between each sample mean and average of all means. Okay. And then I'm just going to follow the normal process for computing standard deviation. So I'm going to take those values, I square each value, I add them all together. So that's what's happening here. So this is just the sum of all of the squared deviations. And then I divide by n and I take the square root. Because we're talking about the population value, so we divide by n in that case. And those definitions are given at the end of lecture set 2. But it's not overly important right now where the formula comes from. I just want to illustrate what's happening. So I have 5 population values. I collect samples of size 2. I enumerate all possible samples of size 2. I find the mean of all 10 sample means and the standard deviation of all 10 sample means. That gives me 3.386, 0.373. So what does this mean? Well, in order to get a better understanding of what this means, we need to consider one more example. So in this illustration, I took samples of size 2 from the 5 values. Now suppose I take samples of size 3 from the same 5 values. So it's the exact same population, but I'm just taking a slightly larger sample size. Okay, so same process. I collect 10 samples because 5 choose 3 is also 10. Listed in the table are the 10 samples. So you can see that I have the sample number and the values that belong to each sample. For each sample, I compute the sample mean, and then I find the mean of all the means. Notice here that this is the exact same value as what was given when the samples were of size 2. Okay. Then I compute the standard deviation of those sample means. Notice now that this is smaller. Okay. So through these illustrations, what I'm trying to show you is how the mean and the standard deviation of the sample mean behave when we collect larger samples from the same population. In the event that we collect a larger sample from the same population, the mean does not change. So regardless of the sample size that we are using, we always have the same mean for the sample means. The standard deviation of the sample means gets smaller as the sample size increases. So what we are trying to establish here are a general set of rules or formula that we can use to compute the parameters of the sampling distribution of the sample mean. And it turns out that when we have a population of interest and we collect a sample of size n, so any sample of any size, the mean of the sample means is equal to the population mean. Okay. And the standard deviation of the sample mean is the population standard deviation divided by the square root of n. Okay. So what this is showing us is that no matter how big or small the sample is, the mean of the sample means is always at the center of the distribution, is always equal to the mean of the population. So this is not affected by sample size. However, the standard deviation of the sample mean will get smaller as the sample size goes up. So the more information we collect, the tighter the bound or the tighter the standard deviation will be around our mean estimate, which is basically saying to us, the more I collect, the better, or the more I collect, the more precise my estimate is going to be, which is typically ideal. It's essentially saying that error goes down with the more information that you have, which is very reasonable. Okay, any questions so far? This is very conceptual for us, but these are these opening key definitions on the third assignment. Okay. Okay, so now we're going to start looking at some exercises that illustrate what we can do with the formula empirically. So question 1A, or exercise number 1. IQ scores for gifted children aged 14 to 17 follow a distribution with mu equals 142, sigma equals 10. All right, so the variable here is IQ scores for gifted children aged 14 to 17. So this is the variable. Okay. Now we're told that this variable belongs to a distribution with mu 142 and sigma 10. So the population of IQ scores for gifted children aged 14 to 17 has a mean of 142 and a standard deviation of 10, which is actually, if you look at IQ scores, quite high compared to the average population. Okay, in part A, it says, what are mu x bar and sigma x bar for all samples of size 50? So this question is asking us, what are the mean and standard deviation of all sample means for samples of size 50. Okay, so this is the same thing as asking, what are the mean and standard deviation of all sample sizes of all sample means for samples of size 50? Now, the most important thing that we can take from this question is that we do not know what the actual distribution of IQ scores is. We don't know the shape. We just know the mean and the standard deviation. But that doesn't matter because those formula that we defined on the previous slide can be used regardless of whether or not we know the shape of the distribution. So to answer this question, we write mu x bar is equal to mu, which is 142. Sigma x bar is sigma over the square root of n, which is 10 over the square root of 50, which is 1.414. And that's it. That's our answer. So the mean mu x bar, the mean of all sample means of samples of size 50 is 142. And the standard deviation of all sample means is sigma over the square root of n, which is 1.414. You may not have to do the math, but you must understand the formula, which is something that Yoda never said. Okay, what if the sample size is very small, like 3 to 5? Yeah, doesn't matter. These formula you can use them in any situation if you want the mean and the standard deviation of the sample mean. And any situation, anytime. In this case, we don't even know the shape of the distribution and we're still using them. That's very important. These are constant across any scenario. These are always true. Okay, part B. What are the parameters of the sampling distribution of X bar for all samples of size 250? What is the variance of X bar? Okay, exercise B is me trying to purposely be confusing. This question is the exact same question as part A. In part A, I ask you directly, what are mu X bar and sigma X bar? those are the parameters of the sampling distribution of X bar. So part B is the exact same question, but we just increased the sample size to 250. Okay, so here we have mu X bar is equal to mu. Notice that changing sample size has no effect on the mean. It's the same. No matter what the sample size is, mu of X bar is always mu. And then sigma X bar is sigma over the square root of n, which is 10 over the square root of 250, which is 0.632. Okay, and then it says, what is the variance of X bar? Okay, well, the variance of X bar is just going to be the square root, or it's going to be the square of the standard deviation. So that's 0.632 squared, which is 0.4. Yeah, so I think to answer your question, the sampling distribution of the sample mean is the distribution that the sample mean follows. And the mean of the sample mean is equal to the population mean. So there's two examples of that shown here. And the standard deviation of the sample mean is sigma over the square root of n, which there's two examples shown here. Does that help? What kind of dog is it? Like it's a mix of those two? It wasn't plugged in when he ate it, right? Oh, pets. Sorry, any questions? I was just gonna scroll on. Yeah. $8.49. I am the slowest teacher in the world. All right. Sampling distribution of the sample mean. Discussion. I'm totally rattled after that dog talk. Okay. So we went through those two examples where we have the formula of the sampling distribution of the sample mean. On slide 10, I'm just recapping how the distribution behaves. So basically, the standard deviation of X bar is a measure that determines how close or far the sample means are going to be from the population mean. So the smaller the standard deviation of the sample mean, the smaller the expected sampling error. The larger the standard deviation of the sample mean, the larger the expected error. It's basically telling us, like if it's small, it's saying everything is close to the mean. If it's far, it's saying all the values are far from the mean. No matter what sample size, the mean of the sample means is the true mean, and the population of the sample mean is sigma over the square root of n. And those formula can be used no matter what. Okay. Okay. In the example that we just looked at, in the example that we just looked at, we applied those formulas shown on slide 11, and we did not know the shape of the distribution. Now, if we know that the population that we are sampling from is normal, then these parameters will parameterize a normal distribution. Okay, this is typically an area where students start to get confused because they think that you can only use these formula if the population is normal, which isn't true. You can use these formula whenever you want. However, if you are able to show or you know that the population that you are sampling from is normal, then these equations give you the parameters of a normally distributed sampling distribution. So the idea here is effectively that normality breeds normality. So if we start with population, okay, so this is normal curve with mu and sigma, and then say we collect a sample. Okay. Because the population was normal, this is going to be a normally distributed sample with X bar and S. And then because the sample is normal, the distribution of X bar, okay, so the sampling distribution of X bar is normal with mu X bar and sigma X bar. Okay, so again, the point that I'm trying to make is the formula for the sampling distribution of the sample mean. So the formula where you don't have to do math, you can always use that formula when you want the mean of all the sample means. If your population is normal, so if you start from normality, you end up at a distribution that is also, you end up with a sampling distribution that is also normal. So normal population leads to normally distributed sampling distribution. And if that is the case, then mu X bar, sigma X bar become the parameters of a normal distribution. Any questions? No, that's not true. So all the sample means are considered as population. That's not, I don't really understand what you're saying, to be honest, but I wouldn't equate the two. The sampling the sample means have their own distribution, which is the sampling distribution, and the population has its own distribution, which is the population distribution. But if the population distribution is normal, we end up with a sampling distribution that's normal. Yes, okay, that is true. So the formula tells us that the mean of the sampling means is the population mean. So that is true, yes. Okay, on slide 12, the illustration here is meant to show us the same concept as what I sketched out on the previous slide. So we're revisiting our substrate concentrations of influent to a reactor. So our variable here is the substrate concentration. We are told in the question that the variable is normal and it has a mean of 0.3 and a standard deviation of 0.06. Okay, so we already know the population is normal. So in this first plot here, this is the population density curve. Okay, so this is centered at mu equals 0.3. Okay, in the next two plots, I have two different sampling distributions. So this is the sampling distribution when n equals 5. And this is the sampling distribution when n equals 20. Okay, so what you can see here is that all of these plots are centered at the same points, right? So we know that the mean of the sampling, the mean of the sample means is the population mean. So that's why all three plots are centered at the same point. But we also know that sigma x bar is sigma over the square root of n. So that's 0.06 over the square root of 5, which is 0.0268. And here we have 0.06 over the square root of 20, which is 0.0134. So what we are showing here is that we start from a normally distributed population. So we know that the variable is normal in the first plot. Then we compute two examples of the sampling distribution of the sample mean. Because the population mean, or because the population is normal, the sampling distribution of x bar is also normal, which is why we have bell curves in plots 2 and 3. As the sample size increases, the bell curve's tails go down and the peak goes up. Sorry, as the standard deviation, or as the sample size increases, the standard deviation decreases. And that's why you have the tails coming in and the peak going up. So what we are showing here is normal population leads to normal sampling distribution. We can apply our formula for the parameters, and we are able to better describe how that sampling distribution is going to behave and get an idea of what it's going to look like visually. So as the sample size increases, you're basically just getting a tighter normal curve. So you're getting values that are closer to the population mean as from the samples that we collect. Okay, any questions? Okay, so on slide 13, I'm just giving some recap of the points that I tried to make using those visualizations, which is essentially that if you, again, like, I can't really repeat this enough because this is going to become a little confusing for students, but if the population is normal, the sampling distribution is normal. In that case, we understand that we are working with bell curves. As sample size goes up, the bell curve gets tighter to the mean, and the mean is always at the same point. So the population and the sampling distribution have the same mean. Okay, the central limit theorem. The central limit theorem is one of the more important theorems that we are going to study in this course. It also is a key definition that I believe you need for assignment 3. Yeah, it occurs in two parts. All right, so in the previous illustration, the main takeaway was that if you start from a normal distributed population, you have a normally distributed sampling distribution. So normality leads to normality. So the question then becomes, what if the population is not normal? So what happens if we start from a population where the values are not normally distributed? The central limit theorem is a theorem that tells us if you collect enough information, so if you collect a big enough sample size, and in this case, that big enough sample size means that you have 30 or more observations, then the sampling distribution of X bar will be approximately normal no matter what population you start from. So basically, what the central limit theorem does is it gives us a rule by which we can say the sampling distribution of X bar is normal no matter what population we sample from. So this is a very powerful rule because it's essentially allowing us to assume normality for the sampling distribution regardless of where we sample from, as long as we collect 30 or more observations. So to illustrate this idea, we can use a very similar plot to what I used back at the start of the lecture. So for example, suppose that this is my population. So very clearly not normal. Okay. All right, now suppose that I start sampling from this population. Okay, so this is going to be sample 1, sample 2, sample 3. Yeah, the sampling distribution of X bar is the same thing as the sampling distribution of the sample mean. Yeah, those are equivalent because X bar is the sample mean. Okay, so we started from a non-normal population and we started sampling. Okay. Now you can see that the samples are going to have the same distribution as the population. Okay, so now we have two scenarios. Okay. Okay, so suppose in scenario 1, n is less than 30. If n is less than 30, then the sampling distribution of X bar is still going to be non-normal. So it's going to be kind of right skewed. If n is greater than or equal to 30, okay, then the sampling distribution will be normal. And it's going to have mean X bar, and it'll have standard deviation sigma X bar. Okay. And this will have mean, mu x bar, standard deviation, sigma x bar. Okay. So that's basically what the central limit theorem is doing, is it's saying you sample from anything, so something non-normal. In this illustration, I used a right skew, but it could be anything that is non-normal. Left skew, right skew, bimodal, trimodal, whatever. If you collect samples where the sample size is greater than or equal to 30, the distribution of x bar, so the sampling distribution of x bar, will be normal. That's what the central limit theorem tells us. If you collect samples that are less than 30, then the sampling distribution will be non-normal, and it'll still be kind of similarly shaped to what we started with. So in this case, kind of right skewed. Okay, any questions? Okay. So on slide 16, I'm just summarizing. Okay, so this goes back to the point I was trying to make earlier. The mean, mu x bar, and standard deviation, sigma x bar, are always there, no matter what the sample size, no matter what the distribution. Those formulas can always be used. But if we know that the sampling distribution is normal, then those parameters become the parameters of a normal distribution. But you can always use these formula. They are true in any scenario. Does that answer your question? Okay, so on slide 16, I'm effectively just trying to summarize the main points so far. So if we start from a normal population, we have a normally distributed sample mean. If I start from a non-normal population, but I collect more than 30 or more values, I have an approximately normal sampling distribution. And that's the central limit theorem. In any case, those formula for mu x bar and sigma x bar can be used. So those are always available, regardless of distributional properties. All right. So now that we have established how we can check for normality for the sampling distribution via the CLT, what can we actually do with our knowledge of the sampling distribution? So in essence, or in short, we can apply the techniques that we learned in lecture set 5 for working with the standard normal curve to the sampling distribution of the sample mean. So for example, let's consider our substrate concentration of influent to a reactor. We know that this is normally distributed with mu 0.3 and sigma 0.06. Okay, so in this exercise, we are working with a variable that is normally distributed. In part A, we're being asked, determine the percentage of all samples of size 15 that have mean substrate concentrations within 0.01 milligrams per centimeter cubed. Okay, so what is this asking us? It's basically asking us the following. What is the probability that x bar minus 0.01 is less than or equal to mu is less than or equal to x bar plus 0.01? So we're being asked, what is the probability if we collect samples of size 15 that our estimates of the mean will be within 0.01 values of the mean, of the true mean? Oh, wait. Sorry, I have that back. what is the probability there? Sorry, it's like this. What is the probability that X bar will be within 0.1 units of the true mean? That's what this question is asking us. Okay, so the phrasing of the question is admittedly a little bit tricky to understand, but this is the probability statement that we are trying to solve. Okay, now this is a normal probability problem. So we know, I guess here. So we know that the sampling distribution of X bar is going to be normal because the population that we started with is normal. Now, what we want to do is move within 0.01 units of that mean. So we're looking for this area here underneath the normal curve. So we want to be within these two quantities. I'm going to make this mu. Okay, so we can start to simplify this problem. So we know that mu is equal to 0.3. So we have 0.3 minus 0.1 is less than or equal to X bar is less than or equal to 0.3 plus 0.01. So this is the probability 0.29 is less than or equal to X bar is less than or equal to 0.31. All right, now we have seen lots of problems like this already. So we have seen illustrations of problems where we have, 3 is less than X is less than 5. And we know that X is normal. So we know that we just have to standardize and go to the normal table. This is the exact same thing. The only difference is that we're working around X bar. But we know X bar is normal. And we know that the mean of X bar is mu X bar. And the standard deviation of X bar is sigma X bar over the square root, or is sigma over the square root of n. So this becomes the probability that X bar is less than or equal to 0.31 minus the probability that X bar is less than or equal to 0.29. Okay, now what we have to do is standardize, can't spell. No, it's not wrong. Okay, let's do it like this. So now what we need to do is compute Z for X bar. Okay, so we know X bar has mu X bar equals mu, sigma X bar equals sigma over the square root of n. Therefore, Z equals X minus mu over sigma. For X bar is Z equals X bar minus mu X bar over sigma X bar, which is X bar minus mu divided by sigma over the square root of n. So basically the point is, in the situation where the sampling distribution is normal, we can apply the rules for finding area under the normal curve by standardizing X bar. And the only difference between what we did when we had X by itself and what we do when we have X bar is that we divide by sigma over the square root of n in computing our Z score. So basically now these statements here become the probability that Z is less than or equal to 0.31 minus 0.3 divided by 0.06 over the square root of 15 minus the probability z is less than or equal to 0.29 minus 0.3 over 0.06 divided by the square root of 15. Okay. That gives us the probability that negative that z is less than 0.65 minus the probability that z is less than negative 0.65. Now all we have to do is look up those values in the normal table. Okay. So 0.65 is shown here. So 0.7442. Negative 0.65 shown here. 0.2578. So we have 0.7442. 422 minus 0.2578, which is equal to 0.4844. So that's actually just a standard probability problem that we had seen in lecture set 5, and the only difference is how we standardize. So when we want to standardize x bar, we subtract the mean and divide by sigma over the square root of n. The only thing that we have to know in order to do this is that the sampling distribution is normal. So if we start with a normal population, the sampling distribution has to be normal, and we're free to do this kind of calculation. If we do not know the population distribution, or the population is not normal, we just have to make sure we collect more than 30 observations, and then we can do this calculation. Sorry, it's 0.2578. Okay, so on Tuesday, we'll do a couple of more exercises to recap this, but they're the same idea as what we saw before, so just normal problems. And then we'll wrap it up with this, and then we'll move on to the next lecture set, which will be lecture set number 7. Okay, so as per usual, if you guys have any questions, please let me know. I have office hours Monday, Tuesday. Assignment 3 is due Tuesday, I believe. And yeah, I think that's it. So I will talk to you guys on Tuesday. Yeah, I'll like I said at the start of class, I'll send out information about the midterm at the start of next week. See you, man. Yeah, so you can finish assignment number 3 at this point. No worries.